we see recordings of the class?
Okay, Shraddha, that's a very good question. But a very simple solution is that you go to MS Teams, the file section. I've saved the file. These are the notes provided by Kundu sir. Okay, these notes are
Yes,
Yes.
ma'am.
provided by Kundu sir. If you see the notes are so well written, you may be thinking that I am just reading out them word to word in the lectures itself.
Okay, ma'am.
Okay, you see that first of all he has defined a relation.
Yes,
What
ma'am.
is an equivalence relation?
Yes,
I
ma'am.
feel that the this language is very lucid, and
Yes,
because
ma'am.
of this notes, you don't have to like write everything down in the class. Okay,
Yes, ma'am.
yeah,
Ma'am, on
yes.
Wednesday, 9 to 10 slot is booked for algebra class tutorial.
Yes, ma'am. I have mentioned in the mail that Wednesday 9 to 10 or maybe 12 to 11 there will be Ritumani sir's tutorial class. It is not
Uh,
confirmed, but these are two possible slots.
so that's what Dheeraj and I talked about. That in the morning you may not have any free slots. Okay,
And please shift in the afternoon.
yeah. So currently I think the time is 12:05. We should start now. We will discuss the rest after the class of the tutorial timing. Okay, so let's
Okay, ma'am.
start.
Yes,
What
ma'am.
we
Okay,
did in
ma'am.
the last lecture. In last class, okay, is this font size okay? Yes or no?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, if this font size is okay, I'll proceed. In the last class, what we did? We defined the following things. We defined what a relation was, and in that we defined what is a reflexive relation, transitive relation, symmetric relation, and antisymmetric relation, right? After that, we defined equivalence relation. Equivalence relation was the one which is both reflexive, transitive, and symmetric, right? Uh,
Yes, ma'am.
I mentioned in the
Yes, ma'am.
class that any equivalence relation will give rise to a partition, and any partition, so equivalence relation, any equivalence relation will give rise to a partition. How? How was that? I didn't wrote it in the class in previous class, so I'll just write it down. Any equivalence relation will give rise to a partition. How? If X is any element in X and we have defined a relation on X, then we see that either any if I take the if I take the set to be all those elements related to X, that means all Y belong to X such that X is related to Y. And if I define this set to be an equivalence class of X, then we see that either for two elements, the equivalence classes are the same or they are completely disjoint. Okay. So therefore, I can partition X. I can write X as union of equivalence class, say X alpha, where all the X alphas are disjoint, right? This is how I can write X into a partition. If I take all the equivalence class, all the disjoint equivalence classes, then that forms a partition of X. That, that is, all disjoint equivalence classes forms a partition of X. Is this fine? I think it should be fine. So, and again, if we are given a partition, if X is equals to union of X alpha is a partition of X, then we can always define an equivalence relation. Okay. How will we define this? Any guess? Okay. So if X and Y are in X, we will define X is related to Y if and only if both X and Y are in the same partition. Okay, same subset of the partition. So is it a relation? First of all, does everyone agree that it is a relation?
Yes, ma'am.
Okay, it is a
Yes, ma'am.
relation. Again, you can easily check that it is transitive. Sorry, if it is reflexive. Why? Because always X is in some partition and X and X are both in some partition. It is symmetric because this condition um, is not dependent of what the order of X and Y is, right?
Yes, ma'am.
Yeah.
Yes,
And
ma'am.
similarly, this is transitive. So this is actually an equivalence relation. After that, what we see? After that, we defined a poset. That means we defined a partially ordered set. How we defined it? It was actually a set equipped with a relation which satisfies. It is a set equipped with a relation that satisfies what?
Reflexivity, antisymmetric, and transitive.
Very
Transitive.
reflexivity,
Anti-symmetric.
Antisymmetric
antisymmetry.
and
Exactly.
transitive.
Very good. So,
Trans.
in relation to poset,
Transitive.
we defined some terms. What were the terms?
Chain, maximal,
Very good. We defined a chain. We defined an upper bound
and maximal.
and maximal element. Very good. So in a poset, we actually see that it does not happen that every element is comparable to each other. Okay, comparable means that either x is less than equals to y and y is less than equals to x. Yeah, if we have a poset, we defined the relation by the symbol this less than equals to. Okay, we defined the relation by this less than equals to symbol. So if either x is less than equals to y and y is less than equals to x, then we say that x and y are comparable. So it does not happen that every pair of element is comparable. If if it happens, suppose we every element is comparable to each other, then we can always arrange the elements, right? That that means we can always arrange the element in a chain like fashion. So therefore, if it happens, we call the poset to be a chain. Right? It was clear. We also see that we can denote finite posets by diagram. How? If we have a finite poset, we can just write anything which is greater than something to be above a particular tree type structure. Suppose we have A, B, some elements, So, and we see AB. That means if I take this set X, I make this its power set of X, and with the order inclusion, this is a poset, right? Very good. Any problem? Someone's mic was on.
या मैम ये जो बीच वाला मतलब AB258 मतलब ये वाला लाइन नहीं आएगा?
Why? Phi is contained in any set.
मैम बट जो हैश डायग्राम होता है उसमें ये रहता है कि ट्रांजिटिविटी शो नहीं करता है.
Pardon?
मैम जो हैश डायग्राम होता है उसमें यह रहता है मतलब कि पहले से प्री डिफाइंड रहता है कि आप ट्रांजिटिविटी शो नहीं करेगा, वो वैसा ही प्री डिफाइंड रहता है कि फाई ए से मतलब कि फाई ए में कंटेंट है और ए बी में कंटेंट है, तो जो फाई है वो ए बी में कंटेंट होगा, ये पहले से प्री डिफाइंड रहता है. मतलब
Okay,
हमने ऐसा पढ़ा है.
hash diagram. Okay, I didn't use the term hash diagram. First of all, thank you for reminding me. It is a hash diagram. So I was actually trying to show that it is related. We can always put it in the tree structure. I forgot it is called a hash diagram, and I don't think this term is used in the book. So thank you so much. So as someone noted out, thank you so much. In a diagram, it is directly saying that this is actually a chain, right? If I take just this one, and this is a chain, so we do not need to show transitive steps. Why? Right. So what is an upper bound? Someone asked me in the beginning that they have doubts in between an upper bound and a maximal element. Okay, so we will again see. So
Ma'am,
yes.
ma'am, I was asking that in above line, you written that if there is going to be every element, if there is a relation between every
Yeah,
element, then
every pair of elements.
ma'am, the example which you have taken is also a form of a chain.
Yeah,
Where a
only the highlighted part is a chain. That means
okay,
okay.
ma'am. Okay.
That means if I take the set X to be phi singleton A B, this is the set with the containment relation. This is actually a chain, not whole power set. I think I should denote this by something, say Y. If I take Y, then Y is a subset of X, right? But Y is actually a chain. Okay. This highlighted
Yes,
part
ma'am.
is green and this is a chain. I'm sorry, I think the way I explained, that is why you have trouble between upper bound and maximal element. I'm sorry and thank you for pointing out that. So let's say we have a chain. Now let's don't take power set. I'll just define a simple X to be some elements A, B, C, D. Okay, I'll take another example. X to have A, B, C, D. We define A, B, C, D. This diagram means what? This diagram means D is less than equals to C, C is less than equals to A, C is less than equals to B. And by transitivity, D is less than equals to A and D is less than equals to B. So this is how I have defined the relation. Okay. Now, suppose I take a subset of this X. Let me define Y to be the subset D and C. Okay, then Y is also a poset. How? D is less than equals to C. So with this relation, Y is also a poset. Do you agree? Yes or no?
Yes, ma'am.
Yes, ma'am.
Fine. Now let me redefine an upper bound. upper bound. So, but how? But upper bound will be of a poset. We can always define upper bound for a subset of a poset. So, if y is non-empty and y is subset of x is already given a poset. These are the assumptions. Then we can define the upper bound, not the, an upper bound for y. So we call an element u in x, okay, u in x to be an upper bound if this u dominates every element of y. If u dominates every element of y. See, this dominates is the word you need to like pay attention to. That means an upper bound is something which want to like dominate everything within the set. So that is why it is called an upper bound. Okay. Can you feel what I'm trying to say?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. Yeah, ma'am. Now clear.
Right. And we defined maximal element. Now maximal element was in any poset. That means if x is a poset, we defined maximal element of x. We call uh, uh, we call an element m in x maximal element in x. So I should just say upper bound of y and highlight this again, upper bound of y and maximal element of x. Okay. Upper bound was for a subset, maximal element is for the complete poset. But what was the maximal element? Maximal element was something which do not want to be dominated. If M does not want to be dominated. So M does not want to be dominated. That means there is nothing above this. So I think I should have left some space. Yeah. So what I'm saying is the maximal elements does not wants to be dominated. Now what does that mean? U dominates everything in y. This meant that u is anything in y is less than equals to u. That means it happens for all y in y and does not wants to be dominated. That means if anything is if m is less than anything, if m is less than equals to x for any x belongings to x, if something bigger than m is supposed to be in the set, then this element x should be equals to m. That means there is nothing above this. Is it clear intuitively what I'm trying to say?
Yes, ma'am.
Yes, ma'am.
Okay. So can you just give me some example?
मैम एक्सक्यूज मी मैम
Yes.
मैम अगर हम y को कंप्लीट x ले उस
हाँ
केस
जी.
में हमारा अपर बाउंड क्या होगा?
So do you think upper bound क्या होना चाहिए? She has a very good question. Thank you for asking, Harsha.
मैक्सिमम एलिमेंट हो जाएगा वो.
कैसे कैसे? अगर हम अब
No, ma'am.
वापस से इसी पे आते हैं, ये वाला ये पोसेट सबको क्लियर है? ये पोसेट में क्या रिलेशन है? What is the relation in this poset? Is it clear to everyone?
Yes, ma'am.
Yes,
See,
ma'am.
if in
Yes,
this
ma'am.
poset,
Yes, ma'am.
I am taking x to be y. Okay, I want to find. So my question is, what is an upper bound for x? This is the question. So someone say,
Doesn't exist,
someone
ma'am.
Doesn't exist.
Does
very
not
good.
exist, ma'am.
So let me give you the reasoning. It does not exist. So it does not exist. Why? Why is it so? Why?
There's no
Why
relation
it is
between
so?
Ma'am,
A and
dominant.
Very good. So you see, an upper bound is something which dominates everything. Suppose, and it is very much clear that this X has two maximal elements. This one and this one. They are what? They are
Maximal.
maximal
Maximal.
elements because there is nothing above them. Okay, there is nothing above them, so therefore these two are maximal elements. But now see, for an upper bound, upper bound wants to dominate everything. So if suppose this happened to be an upper bound, then this should dominate everything. So in particular, this B should also be below A. Does that happen? No,
No, ma'am.
right?
no.
No, ma'am.
Therefore there is no upper bound. So
मैम फिर तो ये मिनिमम बॉन्ड के लिए भी ऐसा होना चाहिए.
मिनिमम बाउंड नहीं बेटा, लोअर बाउंड.
लोअर बॉन्ड है, ओके.
Lower bound is particular example में, in this particular example, see, how we defined upper bound is something that wants to dominate everything. Similarly, we can define lower bound. That means a lower bound should be something which wants to be in the lowest part. That means if anything from the set should be above that. Does that make sense?
Dominated by every element.
So we can say, yes.
मैम कोई भी मतलब लोअर बाउंड अपर बाउंड के लिए वो चेन होना ज़रूरी है क्या वाई को, कि बिना चेन के भी बन सकता है?
अपर बाउंड होने के लिए आप ये कंडीशन देखिए, इट वांट्स टू डोमिनेट एवरी एलिमेंट. दैट मींस it wants to dominate every element. That means this structure should be there. Okay, it's not chain, but it is in fact related to every element of Y. Okay,
मैम अगर ऊपर वाले एग्जाम्पल में हम बी से एक और पास करवा दें एलिमेंट, सपोज ई, और मैम वो ई ए से रिलेटेड ना हो बट वो बी से ऊपर हो, तो उस केस में मैम इसमें कोई अपर बाउंड एग्जिस्ट करेगा?
in this case also there is no upper bound. Why? Because you see,
मैम फिर तो मिनिमम.
E cannot dominate A. To be an upper bound, E should be less, anything in X should be less than equals to E for E to be an upper bound, right? But is A less than
मैम
equals
फिर
to
यहाँ
E?
तो
No.
No, ma'am.
Okay.
मैम फिर तो
Ma'am,
यहाँ
then
ई
E will
मैक्सिमम
not
एलिमेंट
be
कहलाएगा ना.
Okay. Just
maximal
one at a
element.
time. First Shraddha, then Bilal. Okay, Shraddha, is
Ma'am,
this
I
clear?
just
Yeah,
ma'am, it is
please.
clear. Yes, ma'am, it is clear very much. Ma'am, I just have a query. Then in this case, E will not be maximal element also.
Why E is not maximal element? See, now B is not a maximal element because something is above B. Okay.
Yes, ma'am. Yes, ma'am. But E has no relation with A. So how can we say it is maximal element?
Maximal element. Okay, that is the thing. Maximal element is something which do not wants to be dominated. Okay. It does not want anything to be above this. The requirement of maximal element is something that I don't want anything to be above me. But an upper bound is a
Yes, ma'am.
stronger condition. That means I want everything. I want to be above everything.
Yes, ma'am.
Okay.
Okay.
So
Yes, ma'am.
suppose
Clear very much.
you can take a
Yes, ma'am.
historical reference.
Yes, ma'am. Now it is clear, ma'am.
Yeah, because
Ma'am,
suppose it's a
ma'am,
very powerful empire like what? Who
Yes,
attacked
ma'am.
Porus?
Yes, ma'am.
Magadha Empire.
Upper bound has more
Alexander, yeah, he
significant.
wanted everything. So Alexander wanted to be an upper bound. But
ma'am,
Yes,
Porus,
ma'am.
he wanted to be a maximal. That means nothing above me.
Yes.
ma'am, can you repeat the idea of chain? I didn't
Idea
get
of
that.
a chain.
Like I never studied it.
Uh, yeah, please repeat, Mahesh. I was not clearly listen. Mahesh,
Madam, what is chain? I didn't get the chain idea. Like,
chain idea.
uh,
Okay, a chain is something in which every element is related to each other. Okay.
okay, okay,
For example, for a very simple example, if I take R with less than equals to, okay, if I take R with less than equals to, that means X is less than equals to Y if it is less than in the our normal sense. Okay, you can see any element. That is why I can represent R as a line, this sort of line. That means I have R to be totally ordered. I can order every element of the set completely in a chain-like fashion. This is supposed to be a chain-like fashion. If I say, if I take n to n with less than equals to, then I can always say 1 less than equals to 2 less than equals to 3. So it is a complete chain-like fashion. So a chain is nothing but a totally ordered set. Okay, a totally ordered set. That means everything is comparable.
okay,
So
ma'am.
because
I
in
get it.
n with less than equals to, it seems like a chain, and in R with less than equals to also, it's sort of like a continuous chain. So therefore we call a totally ordered set to be a chain. It's just an analog to this.
Ma'am,
मैम
chain
अगर
has at least two elements.
Well, I can take a singleton element and I can just define the relation that it is related to itself. Then it is a poset and a chain, totally ordered, because there is nothing which is of this. It will not be a chain. Our this example is not a chain because
Yes, ma'am.
these two are not connected. These two are not
Yes,
connected.
ma'am.
Okay,
Yes, ma'am.
that means something is
Yes,
off.
yes, ma'am.
Okay, it should not branch.
Yes, ma'am.
Now Bilal was asking something. Bilal, what
मैम ये
is
पूछ इसमें मैं ये पूछ रहा था कि मैम कि ई को मैक्सिमम एलिमेंट क्यों नहीं कहेंगे क्योंकि ये तो बी
E
से
is a
रिलेटेड
maximum E is a maximal element now. अब इस केस में, हम इस नए केस में E को मैक्सिमल एलिमेंट कहेंगे, B को नहीं कहेंगे, E को मैक्सिमल एलिमेंट कहेंगे.
ओके मैम फिर तो पोसेट ए और टी से बनना चाहिए ना मैम
पोसेट
मैम सिंगलटन सेट के लिए फिर मैक्सिमम और मिनिमम दोनों सेम ही होंगे
हाँ, सिंगलटन सेट सब कुछ सेम होगा, सब कुछ. Everything will be same in singleton set. Rahul, you are asking something?
यस मैडम.
Yes.
मैडम जो ये नया पिक्चर आपने बनाया है उसमें अगर हमको ये तो कैंसिल करना पड़ेगा अगर इसको ई को मैक्सिमल होना पड़ा तो.
Yeah, that is why I have crossed that B is not now maximal. The maximal is actually E.
मैडम ऑल्सो वो ए को भी तो हटाना पड़ेगा शायद. ये तो चेन ये रहेगा.
A is maximal because nothing is above A. You see, above A the atmosphere is very clear. There is nothing above A. If we have nothing above A, then it is maximal always.
मैम अगर सेट फाइन एमपीटी हो उसके लिए फिर मैक्सिमम लिमिट मिनिमम लिमिट के लिए क्या कहेंगे?
Please repeat.
अगर हमारा सेट एमपीटी हो तो उसके लिए फिर मैक्सिमल और मिनिमल एलिमेंट के लिए क्या कहेंगे?
See, empty set, if we have an empty set, how will you define a relation? If we do not have a relation, then which is not reflexive, antisymmetric, transitive. If we do not have a relation, then it is not a poset. If it's
मैम अगर
not a
इम्पटी
poset,
रिलेशन हो तो
what is empty relation?
मैम
If there is
इम्पटी
nothing,
सेट इम्पटी रिलेशन पे तो इक्विवेलेंस रिलेशन होता है ना.
okay, so
मैम
everything is
जो
nothing,
रिलेशन होता है
everything
वो
is
ए
nothing.
क्रॉस बी का क्रॉस प्रोडक्ट होता है, तो फाई भी तो उसका एक सबसेट है ना, तो इम्पटी रिलेशन तो होगा ना.
But empty relation of any non-empty set, it is not even
मैम
reflexive. Okay, empty relation. If I take a non-empty subset of an empty set, it is not even reflexive, so it is not an equivalence relation. If I
सेट
take
ही
empty,
इम्पटी ले तो
if we take an empty subset of an empty set, so I'll think about it. So should we just proceed? It's 12:35.
Okay.
Okay. So after poset, what we did is we defined
Hello,
John.
ma'am.
Yeah. Yes.
Ma'am, can we say if an element of a poset is upper bound, which implies it is a maximal element, but not conversely?
See, when you say upper bound, what he is asking is, suppose, I'll just repeat. He says that suppose I take y to be x, and if u is an upper bound for x, does this imply u is a maximal element?
Yes.
Yes, definitely.
Yes.
Okay. Now he was asking, it is not otherwise. Converse is false. That means he's saying that if maximal, u is maximal, m is maximal, that does not implies that u is an upper bound for x. Maximal in x and upper bound for x. That's very much clear from our example because we have two maximal elements. They are not related. So that cannot be an upper bound. Okay.
Ma'am, if there is unique maximal element, then can we say that this is upper bound?
Then also we unique maximal element. No, we cannot say this.
मैम मैक्सिमम एलिमेंट तो एक से ज्यादा भी हो सकते हैं.
No, his query is unique maximal element. Unique.
मैम यूनिक मैक्सिमल तो ग्रेटेस्ट एलिमेंट बन जाएगा ना, फिर वो अपर बाउंड क्यों नहीं होगा?
Unique maximal element. So should I reply this or should I give you some time? I think I should give you some time to construct a counter example. It's very easy to construct a counter example. Does this implies upper bound in X? Okay. This does not happen. Answer is no. Okay. I'll leave this for you to construct. If you cannot, then I'll reply again. Okay.
Ma'am, counter example has already given above.
Yes,
E
ma'am.
is maximal
Last
element,
example.
but it is not upper bound.
E and A both are maximal again.
Yes, ma'am, and both are not upper bound.
It's
No.
not
But the
unique.
question is it's for unique, na?
Unique. Beta unique.
Ma'am,
Okay,
can
okay.
you say upper
Can
bound
you
doesn't
please
belong to
just
the set?
now? Beta, can we just stop with this discussion because we are running out of time. I have not started lecture 2, which was supposed to happen.
Yes, ma'am.
Please keep these
Yes,
questions
ma'am.
for the tutorial
Yes.
class. Okay.
Yes, ma'am. Yes.
Okay,
So
ma'am.
now after that, what we stated was Zorn's lemma. So I think I have emphasized quite enough that it is very much important. It's a very important mathematical tool. Okay, what did Zorn's lemma said? Zorn's lemma said that if every chain, that means if every chain, we can also say chain to be a toe set. Okay, totally ordered set, toe set. So if every toe set or chain in a PO set, that means partially ordered set, has an upper bound, then X, the PO set X, has a maximal element. Does anyone has any problem in understanding the statements of Zorn's lemma?
No, ma'am.
Okay.
No, ma'am.
Okay, thank you. So I asked all of you to just do an application of Zorn's lemma, right? I asked you to just write down an application which says that every vector space, whether finite dimensional or infinite dimensional, every vector space has a Hamel basis. There always exists a Hamel basis. Did you do that?
What is Hamel basis?
Hamel,
मैम
Hamel
हैमल बेसिस क्या
basis.
होता है मैम? बेसिस पढ़ा है?
No, your normal basis, okay? This will be clear in maybe next year. Yeah, just a basis. Every vector space has a basis. Next year when you will take a functional analysis course, 6012 something, I don't remember. There it will make a sense. Okay. I think you have not done it.
Yes, ma'am. I've done it.
Very good.
Yes, ma'am. Me also.
Very good.
Yes, ma'am.
Okay, fine. So because we have to start lecture 2, I'll leave this discussion now. Now we move on to countability. In this, what we did, we defined a finite set. Anything which was not finite was infinite, right? But in infinite, we wanted to understand what is a smaller infinite sets. What is a smaller infinite set? Just like n, and we want to differentiate it from larger infinite set, which was like R, right? To make this distinction, what we did is we defined countable set and uncountable set, right? So we want smaller infinite set to be countable set. So that was our intuition. That means we can always say that the elements of this set, we say X is a countable set if we can define a function from X to n to X, a bijective function. That means 1, 1 and on 2. So this is actually saying that I can arrange X as x1, x2, dot, 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 where x1 is nothing but f1, f2, and so on. So countable sets.
मैम इंटीजर का
Yes, Bilal.
इंटीजर का सेट काउंटेबल होता है अनकाउंटेबल?
Yes, it is countable.
मैम फिर इसके हिसाब से तो नेचुरल नंबर जो हमारी मैपिंग होगी वो 1 1 2 नहीं होनी चाहिए क्योंकि नेचुरल नंबर छोटा हो जाएगा.
That's very bad. We will call X to be a countable set if there exists some function which is 1 1 and on 2. Okay, And if this happens, we can always write down x. This is called enumeration of x. Now he's saying that z cannot be countable. So I can define a function from n to z. How? I can define a function 1, 1 and on to f of 1 to be 0, f of 2 to be 1, f of 3 to be -1, f of 4 to be 2, f of 5 to be -2, and so on. This way I can, this mapping, if you just like, I don't just recall its relation, I can always define such a mapping which is 1, 1 and on to. Therefore, z is countable. Okay. Such type of questions and much more difficult questions, like difficult than z actually, not so much difficult, are in the tutorial sheet. Okay. So I request you all to kindly go through the questions. The questions in tute sheet 1, the question number 1 to question number 7. They are all about whether a set is countable or not countable. So I request you to go through those questions, and in any of that case, if it is not countable, how will you show that not countable? So any set which was not countable was uncountable, right? If x is not countable, then that means there, if I take uncountable set, this means that there does not exist any bijection between x and n. That means if I take any function from n to x, it can't be either 1, 1 or on 2. So actually it cannot be on 2. F cannot be on 2. Fine. Such an examples are in the tute sheet, which we will discuss in the tutorial class. Bilal, is that fine?
Yes, ma'am.
Okay. So now we have a distinction between smaller infinite set and larger infinite sets. So after that, I'll just move on to. Oh, I think something is left. Yeah. Now there are two important principles. So do you have a class after this?
Yes, ma'am, but it's at 2.
At 1 o'clock.
Okay, so can I take 10 minutes extra if that's fine with
Yes,
you?
ma'am. Yes, ma'am. No problem.
Okay, okay.
Yes, ma'am.
Thank you so much. So now, when we talk about natural numbers, the well ordering principle and the principle of mathematical inductions comes naturally. So I'll redefine what a well ordering principle what the well ordering principle was. Okay, so well ordering principle of natural numbers says that any non-empty subset of n has a least element. Okay, so before well ordering principle, I'll define a least element of n. Suppose we take S to be a non-empty subset of n. Okay, we say S has a least element if uh, so let's just see it again. Recall that n with this type of relation, this is actually what n with less than equals to was a poset. So if I take any subset, that will be also a poset. Sorry, that will, any subset of n will be a chain because n is a chain, right? So
Yes.
Chain, in this chain, the least element is actually the lower bound. Okay, the lower bound which we were just imagining, the least element is something has a least element S if S is less than equals to everything in the set. I should just make this L. Okay, least element L if L is less than equals to S for all S in S. Okay, is this definition clear?
Yes, ma'am.
So we
Yes, ma'am. Yes, ma'am.
well ordering principle actually says that this least element will always exist. Okay, well ordering principle just says that and this least element is unique. If L exists, then L is always unique. Okay.
Okay, ma'am.
Okay,
Yes,
well
ma'am.
ordering principle just says that if I take any non-empty subset of n, then it will always have a least element. Every so you seems to think that come on, it's like there you can see. Every non-empty subset of n has a least element. Okay. Now, do you
Yes, ma'am.
remember principle of mathematical induction, PMI?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay.
Ma'am,
Principle of mathematical induction, yes.
ma'am, when applying well ordering principle, ma'am, the
Yes.
set should be totally ordered. On which set we are applying well ordering for
We are
n, for n it
n.
is okay,
Well
ma'am.
ordering principle of n. We're
Okay,
not
ma'am.
talking about anything else, just n. Okay.
Yes, ma'am. Thank you.
So what I'm trying to say is well ordering principle and PMI are nothing but the same. My claim is that this well ordering principle holds if and only if the principle of mathematical induction holds. That means the both of them are in fact the same. While solving questions using principle of mathematical induction, what we all use to do that? We say Pn is a statement. That means some statement is true for some n is n. For n belongings to n, we say Pn is true if some statement is true for n. Some relation involving n. So in order to prove that this statement is true for all n, we wanted to prove in order to prove Pn is true for all n, we usually show two things. Number one, that means P1 is true, right? And number two, Pn is true implies Pn plus 1 is true. This is what we used to do. I think this is clear. Okay,
Yes, ma'am.
the principle of mathematical induction actually says that if I take S to be a subset of n, if S is a subset of n, such that two things holds. Okay, such that one is in S and n belongs to S implies its successor n plus 1 belongs to S. Then S should be equals to n. Okay.
Yes, ma'am.
Yes, ma'am.
So
मैम नेचुरल का मैम
yes,
यहाँ पे एस एम्प्टी सेट भी ले सकते हैं
S हम कुछ भी ले सकते हैं. नहीं नहीं नहीं
मैम
नहीं
फिर उस
नहीं. Non-empty set, non-empty set. Sorry. One is in S, that means S is non-empty.
ओके मैम
है ना? This condition ensures S is non-empty. And second one says that if something is there, then its successor should always also be there. Okay. Now we can easily prove PMI using well ordering principle. Well ordering principle implies PMI. How? Suppose X now if I want to prove this thing, suppose S is not equals to n, then what happens? That means S is a proper subset, right?
Yes, ma'am.
Yes, ma'am.
S is a proper subset. That means n minus S. N minus S, suppose I denote it by T.
Non-empty.
Then T is non-empty. Very good. If T is
Yes, ma'am.
non-empty, then well ordering principle says what?
इसके पास फिर
It
लिस्ट
has
एलिमेंट
at
होना चाहिए.
least one least number.
एलिमेंट
That
होना
means
चाहिए.
very good. Well ordering principle says that now T has a least element. WOP implies T has, capital T has a least element. Unique least element actually.
Yes.
That means say L, that means L is less than equals to T for all T in T. Right? But T was what? N minus S. This actually implies that L minus 1 does not belongs to T. L is less than equals to T for all T in T.
Yes,
We
ma'am.
know that L minus 1 is less than equals to L. Therefore, L minus 1 is not in T. But what does this statement says? If L minus 1 is not in T, this implies actually by definition it is in S. But condition number 2 says that if n is in S, n plus 1 is in S. This implies L minus 1 plus 1, which is nothing but L, is also in S. Does that make sense? L was an element in T which was complement of S in
Yes.
L. This
Yes, ma'am.
happens to be a contradiction. So similarly, it is a very easy proof for PMI implies WOP. That means principle of mathematical induction implies well ordering principle. I think I'll leave it to you. If it is not clear, then you can ask us in the tutorial class. Okay. Now we move on to Cartesian product. See, I am defining Cartesian product. I think in the previous class I told you that these are nothing but preliminaries. You should know Zorn's lemma, well ordering principle, axiom of choice, right? These are some underlying principles. Similarly, like Zorn's lemma is equivalent to actually. So what I'm saying is Zorn's lemma is actually equivalent to well ordering principle and principle for R, not N, and which is equivalent to axiom of choice. And all of them are actually very important in proving existence of some things. Just like existence of basis for any vector space, there are very many existence theorem in mathematics, in analysis actually. So these are the preliminaries to understand axiom of choice. We will define what an axiom of choice is, you will be very clear that it seems to be trivial, but actually they are not provable. There is no proof for them in the literature. Something implies something is there, but no complete proof. Okay, so in order to just appreciate its beauty, you want applications which will come later on in your any analysis course. I think I have said this statement maybe 10 times. So let's now move forward. I'll define a Cartesian product. Cartesian product or simply product. Suppose I have two sets, x1 and x2. Okay, I define x1 cross x2, the Cartesian product. How have we defined? We have always defined it as tuples, right? Small x1, small x2, such that x1 is in x1 and x2 is in x2. This is the way we have always defined the product of two sets. Cartesian product of x and x is defined to be these sets, right? We have similarly defined the Cartesian product of finite number of sets, x1 dot dot.
Yes, ma'am.
Right? You all know that we have always defined such things. But now I want to ask, suppose I have not say finite number, suppose I have an infinite number of sets. Suppose I have defined x alpha for all alpha in R. Suppose I have these non-empty sets. Suppose I have this collection of sets. how will I define their product? So question is,
Alpha belongs to R or alpha belongs to M?
sorry, real numbers, a very large collection of sets, very large collection of sets. You know that it is a very large collection of sets. So I want to define their product. How will I define it? Now the
Ma'am, alpha
problem
की value
is,
of 1.
Ma'am,
Value of
how
1.
can alpha belongs to R?
मैम
मतलब
अल्फा
index
तो
set
एक इंडेक्स है मैम.
okay, I am saying I have a non-empty collection of sets phi. I have a non-empty collection of sets for every alpha in R. Does that make sense?
मैम अल्फा तो इंडेक्स है ना, ऐसे तो काउंटिंग नहीं करे जाएंगे ना, 1/2 तो ले सकते हैं, अल्फा 1/2
Exactly. We have a problem here. We just don't know how to define the product in terms of what we have defined for a finite set. Right now I have a uncountable number of sets. I don't know how to define a product because my definition of product is inherently dependent on a particular order of these sets. Right? Because my definition is dependent on a particular order of the sets, therefore it is impossible for me to define the product in such fashion. So I have to, so a solution for this problem is actually we need to redefine the product for finite sets. Redefine the product for finite sets. I want to redefine the product such that the definition now becomes order independent. If I take any order of x1 and x2, my definition should become independent. I want to redefine that such that the new definition becomes independent of the order of sets. Right? This is my aim.
Yes, ma'am.
Yes, ma'am.
Very good. But how will I do that? Now see, if I take x1, x2, xn, where xi is in capital Xi for I from 1 to n. Now I can see is this is something, some position, first position, this is second position, this is nth position. So basically an element of the Cartesian product, I can say this is some sort of a function from 1 to n to union of xi. Some specific function from 1 to n to union of xi, I going from 1 to n. Okay, I am saying that an element is a specific function, an element of the Cartesian product. Okay, I will not say, I'll just drop the word Cartesian. An element of the product x1 to xn can be seen as a function from 1 to n to union xi, I from 1 to n. Why I'm saying that it is a specific function? I think I didn't wrote specific. What is the specific thing about this function? A specific thing about this function is that f of 1 should belongs to x1, f of 2 should belongs to x2. Similarly, f of n should belongs to xn. This is a specific thing about this function. So in this way, I can see x1 to xn to be collection of functions from 1 to n to union of xi, I from 1 to n such that f of I is in capital Xi for all I. Is it clear?
Yes, ma'am.
Yes, ma'am.
Okay. So now if you see this definition now becomes
Ma'am,
order independent. Yes?
ma'am, this F1, F2 is also in form of a order.
Now I'm not saying it is in any form of order. Okay.
Means whenever we are taking the Cartesian, whenever we are taking the product at that moment for the every single position,
Now see,
means
I will not write it as this thing. I'll write it as product Xi, I from 1 to n. Now this 1 to n becomes the index set. Okay. This 1 to n.
yes, ma'am. Okay.
मैम ये एक बार समझा दीजिए ना ये फंक्शन वाला.
ठीक है. So what is happening is I am defining a function. So again, I have taken an element from the Cartesian product. From this Cartesian product, the way we have defined, I have taken an element, right? Now this element, I want to re-examine this so that I can define the product independent of the order, right? We have specifically listed x1, after that x2, after that xn, right? This is the order which we have followed. So I am saying that x1, that means first position, x2, that means second position, and xn means nth position. So I can say that if I can say this element is nothing but a function from 1 to n to union of xi. And because this domain is finite, the domain of this function is finite, I can describe f by simply listing out its value. So I can describe f by listing out its value, right? Listing out its value, that means f1, f2, dot fn, which is same as x1 to xn. Okay. Now in this way, I am saying that I am identifying an element, this one, I am identifying this element to be a function. Okay. Is it clear now?
Yes, ma'am.
Yes, ma'am.
Okay. Now the domain of this function is called the index set. This domain of the function is called index set. So whatever index set is given to us, I can define the product independent of the order. Okay. Independent of the order of the elements in the tuple.
Yes, ma'am.
Okay. So actually the index set is something which is used to identify the family of sets. This we have oh, what happened? Yeah, we are given a finite family. So that means the index set was nothing but 1 to n, right? And in that way we have defined the Cartesian product as a collection of functions from the index set to union of xi. See now, the index set is nothing but something which is used to identify sets in the family whose product we want to define. Okay, we want to define a product in family, and this family we denote by the index set. Okay, if in this family you can see that one is used to identify the family. What I'm saying is one is used to identify the set x1, the set x1 in this family. Okay, n is used to identify the set xn in the family. So in this definition, what we defined the Cartesian product, the fixed position order, we just replace it by a particular index set. Okay, so that is actually a one-to-one correspondence between the index set I and the corresponding family of sets. Xi. Okay, I belongs to I. The index set is just coming out from the family of sets whose product we want to define. Do you understand?
Yes,
Yes,
ma'am.
ma'am.
Okay. If there is any problem, then just you can ask again.
That is मैम हमने जैसे कि स्टार्टिंग में लिया था x अल्फा और अल्फा बिलोंग्स टू r देन देयर मतलब
या अल्फा r प्लीज अभी रुक जाइए r बस ये फाइनाइट केस में समझ आ रहा है.
Yeah, ma'am.
In the
Finite
finite
case is
case,
easy.
from a ordered tuple, we move on to functions. It was quite easy. We just take the family. How are the elements of the collection of sets defined? The index set. We identify the index set. There should be a one-to-one correspondence between the index set and the family of sets. After that, we have the one-to-one correspondence. I can simply say that we can take just the collection of functions. I am just taking this collection of functions from the index set to the union of all the families, but with a restriction. We have a restriction. A restriction is there. Restriction is there on F, right? What was the restriction? Restriction was that Fi should belongs to Xi for all I in capital I. Right? We had a restriction.
Yes, ma'am.
The domain of F was I. Its range was union of Xi, but it cannot we cannot take just any arbitrary function. We have a restriction. So if we have such a restriction, we call F to be a choice function.
मैम आई इंटीजर है यहाँ पे नेचुरल नंबर.
हमने अभी जो डिफाइन किया है, हमने I को जस्ट लिया है 1 to n for some fixed n.
Okay, ma'am.
Okay. Now the
Yes, ma'am.
definition of function is independent of order. We have a restriction, but the definition becomes independent of the order.
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
I'm saying that such a function from index set to union who satisfies this restriction condition is called a choice function. Okay. So now in this way, I can define a product of arbitrary family of non-empty sets. Now suppose Xi with the index set I is an arbitrary family of non-empty sets. Okay, if we have an arbitrary family of non-empty sets, then I can define their Cartesian product. That means product of Xi, sorry. Yeah. Their Cartesian product of Xi with I belongs to I, the index set, to be collection of all the functions from the index set I to union of Xi such that I is in I, such that f of I is belongings to capital I for all elements in the index set. Simple. This is how I am defining.
Yes, ma'am.
Okay. Now the definition becomes order independent. Now any index set you take, if you want to take natural numbers, you can take natural numbers in this definition. Finite set you want to take, finite set you can take. If you want to index by real numbers, you can index by real numbers. It's definitely up to you. But there is one problem I see. We know that all xi's are, I'm taking all xi's to be non-empty. And I'm defining product of xi to be collection of functions which satisfy this condition. But the question becomes, does there exist at least one choice function? Does there exist at least one choice function? Now you will argue that, okay, we can take every non-empty set. Oh, sorry, if everything is non-empty, we can just keep picking elements from each xi, right? Just like in our finite case, we can just pick each element from xi. If all the xi's are non-empty here, I can always say that one choice function exists. Just pick one element from each xi. But the problem is, for saying that a choice function exists, this process of picking, for a choice function to exist, the process of picking elements should be complete in a finite time. That means you cannot keep on picking elements infinitely time. Do you understand what I'm trying to say?
Yes, ma'am.
No, ma'am.
Okay, so I am
मैम बहुत था
saying,
आज के लिए
okay,
खाना
Ma'am,
भी खाना
continue,
है
ma'am, continue.
कुछ समझ में नहीं आ रहा
I think I'll just finish this one because the next class will be of Professor Kundu sir. Okay, in that class he will only explain axiom of choice. He is definitely going to repeat everything which I am saying about the Cartesian products. Okay, he will definitely repeat everything in order to tell axiom of choice. But I'm saying that, does there exist at least one? So what I'm saying is, suppose I have you have R2, you know that there R2 is non-empty. There exists one choice function. You know that if I take Rn, there exists at least one choice function, right? But if I am saying that if I take collection of R, X, I have R to be R times. Do you understand?
Ma'am, what do
Yes,
you mean
ma'am.
by choice function?
Choice function, that means an element in the product. An element in the product, that means a function from the index set to union, a function from index set to the union satisfying a restriction condition. That means an element in the product space. The product space which we have defined. So the question becomes, is the product space non-empty? Okay. If we have non-empty collection of sets, is the product space non-empty? Does there exist at least one such function? Okay. I'm asking, does there exist at least one function? So just like in R2, Rn, you say this like take one element, take one element. That means you are picking elements from each of the non-empty set to say that such function exists. That's what I'm just saying. If not, you just try to think. So I'm saying if this, for a function to exist, picking should be complete in a finite time. So the axiom of choice is nothing but it says that there will always exist one. Just that's it. Axiom of choice says that there will always exist one. But the interesting part is that we cannot prove this thing. Do you understand?
मैम ये इसलिए है क्योंकि इसमें इंडेक्स सिर्फ नेचुरल नंबर को ले सकते हैं ना, इसके हिसाब से क्या है?
Pardon?
जैसे इसमें सिर्फ एक ही चॉइस ली जा रही है, वो नेचुरल नंबर के हिसाब से कह रहे हैं ना हम कि नेचुरल नंबर के अलावा कोई और सेट नहीं ले सकते चॉइस में। जैसे अल्फा बिलोंग्स टू आर था इसमें। तो ये सिर्फ उसके लिए क्या है, ये अपनी तरफ से कुछ केस बना के लिया है ना कि नेचुरल नंबर के हिसाब से कैसे कि x1 x2 x3 जैसे x1/2 नहीं ले सकते यहाँ पे।
हाँ
तो सिर्फ यहाँ पे नेचुरल नंबर के लिए ही कह रहे हैं ना यहाँ पे कि सिर्फ नेचुरल नंबर का सेट ही होगा चॉइस में, तो सिर्फ एक ही होगा।
हाँ एग्जैक्टली सिर्फ एक नहीं, कि मैं कह रही हूँ कम से कम एक तो मिलेगा ही मिलेगा। अगर मेरी फैमिली फाइनाइट है तो एक ना एक चॉइस फंक्शन तो डेफिनेटली मिल रहा है।
Yes,
If
ma'am.
I have a
Finite के लिए तो
finite
एक होगा।
collection, then there always exists a choice function there. That means the Cartesian product of a finite family is always non-empty. That is for sure. But is the same thing true for an arbitrary family? To say that one element
मैम
is there,
सिर्फ
the picking of elements for that particular choice function should be
मैम ये सारे
complete
सेट
in a
नॉन
finite
एम्प्टी और
level.
तभी ट्रू होगा ना ये।
हम non-empty लेके ही चल रहे हैं।
अच्छा ओके।
Okay? So exam of
मैम
choice.
अगर आर्बिट्री लेंगे हम तो वो तो कभी कंप्लीट नहीं होगा ना उसमें पिकिंग वाला प्रोसेस।
एग्जैक्टली कभी कंप्लीट नहीं होगा, इसलिए हम इस चीज को ट्रू मान के चलते हैं। The picking will not be in a finite time. It will just continue to go on. So its answer is not there. Like we do not know how to prove this, but it seems that it is always there. This affirmation, that means this mentality that we will assume that such a statement is true. Its true answer, we will assume this. Okay, and this assumption is exactly called axiom of choice. Axiom of choice, that means there always exists one choice function for a non-empty collection of functions. That means if xi, I belongs to I, is a collection of non-empty functions, is a collection of non-empty sets, this implies the product of xi is non-empty. Okay, this is called the axiom of choice.
मैम एक मिनट मैम, अगर हम लोग फाइनाइट सेट का कलेक्शन ले तो उसको तो हम प्रूफ करने की कोई एक फंक्शन में बना सकते हैं हमेशा, बट अगर हम लोग आर्बिट्री ले पर हम लोग कभी दिखा नहीं पाएंगे कि वो चॉइस कभी कंप्लीट होगा, बट हमें पता है कि चॉइस बन सकता है, इसलिए प्रूफ नहीं कर सकते।
ना हमें पता है ना, वो हमें इंट्यूशन आ रहा है कि बन सकता है।
हाँ, लेकिन ये प्रूफ नहीं कर सकते हम।
ये अभी तक किसी ने प्रूफ नहीं किया है। We cannot prove it
मैम
actually.
जैसे इसमें मतलब इवन ओड भी ले सकते हैं। अभी तो पूरा नेचुरल नंबर ले रहे हैं 1 2 3 4 5, इसमें 2 4 6
कुछ भी ले सकते हैं, इंडेक्स सेट है वो, इंडेक्स सेट कुछ भी हो सकता है। यस
मैम, तो इसलिए फिर कह सकते कि एक एटलीस्ट वन तो है ही, लेकिन इससे ज्यादा भी हो सकते हैं इसमें।
तो
हमें
हमें
ओड हो गया, जैसे प्राइम नंबर भी हो सकते हैं यहाँ पे,
कुछ भी हो सकता है इंडेक्स सेट, प्राइम नंबर्स और 4 के मल्टीपल, 5 के मल्टीपल्स, कुछ भी। So axiom of choice is our assumption that this is true. There always exists a non-empty choice function. Axiom of choice is nothing but it says that it should be there. And the interesting part is axiom of choice is equivalent to John's lemma. We cannot prove anything, but we can prove that one implies other and other implies this one. Okay, I think that's it for the today's class.
Okay.
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 Yes.